So before I start, I'd like to thank Suvrat and Loganayagam for his invitation to talk at this forum. Very happy to be here and to share some of my recent research, which is the purpose of this kind of meeting. So it's all quite informal, and I'd be quite happy to take questions as we go along. What I want to talk about is a slight generalization of the notion of Wick rotation, which is something that everyone uses. Everybody here has used this idea sometime in their life, so it's of wide general interest. And the generalization consists of using slightly less structure than is usually assumed in the process of Wick rotation. And the results are going to be applied to some special cases, and just to illustrate the way that it works. So the whole thing is going to be very elementary, accessible to everyone. And I hope that it will, well, it'll raise some questions from the students, as Rajesh was talking yesterday. I'm pretty sure that there is nobody here who has not used Wick rotation at some time in their life. Is that correct? I think everybody here has at some point or the other Wick rotated. Now, what I'll do is to get the some historical background. This is a picture of Wick here. On his left is Enrico Fermi. This is Giancarlo Wick and Eduardo Amaldi. This was taken in 1936 in Europe. And he was part of the gang that was around Fermi, and they were doing theoretical physics in Italy. And I think that although Wick appears several times in most field theory textbooks, most people don't have much of an idea. In fact, I didn't know that he was an Italian until very recently, because the name doesn't sound Italian. I mean, the first name does sound Italian, Giancarlo, but not the last. So I'll start with some very elementary examples of Wick rotation. Giancarlo. Yeah, and actually, as Nanendo's pronounced it, it should be Wick and not Wick, because the Italians would stretch the E around. Oh, sorry. So this is an example of Euclidean methods in physics, and it connects Minkowskian problems to Euclidean ones. What we do is to take the time coordinate and rotate it to imaginary values. This should be thought of as a mathematical trick, kind of analytical continuation. So by using this trick, there are many problems that get related to each other. For example, the Schrodinger equation is related to the heat equation, and the heat equation is the same as the equation describing Brownian motion. You can also relate the thermal fluctuations of DNA, which is an elastic problem. It's a problem in thermodynamics and elasticity, to quantum mechanics, quantum fluctuations of torques. And in fact, that's a topic in which I've worked for a while. So this is also a context in which it is useful. These are a few random examples. One also connects field theories to stat-mech problems. And this is based on the similarity between the Schrodinger evolution operator and the partition function of statistical mechanics. So here is an example of a problem which involves tunneling over a barrier. You start with a particle which has got an energy over here, the red line, and it's sitting in this potential, the potential is high enough that there's insufficient energy to cross it. But if you wanted to work this out, you can go to Euclidean time, and that effectively inverts the potential. It makes the whole problem look like this. You can go from here to there in imaginary time, and you get a perfectly respectable solution of the equations of motion in imaginary time. That solution is called an instanton, and it gives you the exponentially small tunneling amplitude to get from here to there. So in the complex time plane, what you're doing is, instead of going along the real axis, you're going up along the imaginary axis. Usually there's an integral involved, and the process consists of rotating the contour from the real to the imaginary axis, taking care to avoid poles or to take them into account if they're there. So similarly, one can consider the motion of a classical particle in an oscillator potential. One gets periodic functions in time, in real time. However, a real pendulum has a potential which is different from the harmonic oscillator, and it has the possibility of tunneling over the barrier. in imaginary time, it's possible, even with insufficient energy, to go over the barrier, and we get motions with an imaginary period. Now, this directly leads to the theory of elliptic functions. So the whole idea of Wick rotation is related to doubly periodic functions in the complex time plane, and that's basically the theory of elliptic functions. So in quantum theory, these solutions that tunnel from one point to another, they would be instantons. They're solutions of the Euler-Lagrange equations in Euclidean time. Suppose I consider a potential that looks like this. It's a potential which is similar to the earlier one, except that x is no longer periodic. You have the vacuum modified by tunneling effects, and the true vacuum is revealed only by these non-perturbative instanton effects. The Yang-Mills vacuum is also affected by Euclidean solutions of the field equations, and this leads to the idea of theta vacua, and instantons are an important part of the whole story in Yang-Mills theory. Now, everything I said so far had to do with Newtonian physics, where there is a single notion of time, which everybody has. This is the absolute time of Newton. Now, when we get to relativity, the situation gets slightly more complex, but not out of hand. What happens here is that time is not universal, and there are several notions of time, one for each inertial observer. If you stick to the family of inertial observers, each guy has a time. And one can choose the time of any inertial observer and use that person's time to Wick rotate. So it's a matter of choice, which one you want to use. It turns out that the choice doesn't matter. That's why I said it's innocuous. So it converts oscillatory expressions to exponentially damped ones. You can replace the Fourier transform by the Laplace transform. And these are the very common integrals that one gets in optics, for example. They're called Fresnel integrals. Such integrals can be replaced by Gaussian ones, which are easier to deal with. So what happens in special relativity is that it doesn't matter which observer's time you choose. So in a sense, Wick rotation commutes with the Lorentz transformation. So that's why one is able to get away with choosing any one time and going away and using that. Now, this is the context in which Wick originally proposed the idea of Wick rotation. It turned up in quantum field theory, and as you will learn in an elementary course, there's a problem with the propagator in the sense that it has poles. And those poles have to be circumvented, and it's a prescription due to Feynman for avoiding the poles in the propagator. And this is usually done in the energy plane, but what I'm talking about is real space. I mean, not energy, but time, the conjugate variable. So you get thermal Green's functions, which are periodic in time, with a period beta, which is the inverse temperature. And what happens when you Wick rotate is that time becomes a cyclic variable. For example, if I were to apply Wick rotation to this clock right here, which is keeping time, the time would become imaginary, and there would be 36 minutes of imaginary time. It also means that the two ends of my talk would get identified. So you guys would be sitting here forever if I Wick rotate this clock. This beta is the inverse temperature. When you get to relativity, the whole situation gets slightly more complicated because there is a multiplicity of times. In fact, a lot of GR literature is dominated by the problem of time. The classical approaches to quantum gravity were all plagued by the quantum of time. The problem of time, which is coming up because there's lots of times. Everybody has its own time. It's not just an inertial family, but a huge set of possible times. So Einstein, well, let me just choose units in which the fundamental constants are put to 1. We look at Einstein's view of GR, of gravity, is that it's the geometry of space-time. It predicts black holes and many other things like gravitational radiation, on which there's a conference going on right now. In particular, it predicts the Schwarzschild black hole, which is a static object, and the Kerr black hole, which is a rotating object. So let me explain these two words, which I put in red here. A static space-time is one, both static and stationary spacetimes are in a sense time independent, in the sense that they have a time-like killing vector. Let me just gloss over some subtleties here. Suppose you have a Killing vector xi. What it means is that the metric is derived by that Killing vector. If the Killing vector xi is hypersurface orthogonal, then you say that it's static. But if it only satisfies this condition and not this, you say it's stationary. So what this means is that you take the integral curves of this vector field and look at the tangent spaces orthogonal to it. If they mesh together to form a surface, you say it's static. Otherwise, it's stationary. Physically, what this means is that, well, in electrodynamics, you have the notion of electric as well as magnetic fields. And as is well known, magnetic fields are not time reversal symmetric. They change sign when you change the sign of the time. So what happens is that in a static space-time, the magnetic field effectively vanishes. So there's an analog of magnetic and electric fields even in gravity, which is based roughly on this idea. And a static situation is time reversal symmetric in the sense that there's no magnetic field. Whereas the analog of a magnetic field in relativity is rotation. So a black hole which is rotating is not invariant under time reversal. And therefore you have you have something which is where the notion of time is slightly more complicated than in a static case. In a static case, you take the Killing vector field and you can use it to define a time via this formula. So the Killing vector actually gives you a notion of time which you can use for Wick rotation. Now, as I said before, the notion of time takes a real beating in general relativity. There are many different times, and we have to have some criterion for picking up a time. And within GR and quantum mechanics, time has an entirely different character, which is part of the reason why there's so much conflict between the two theories. Now, to switch gears to a slightly higher plane, Hawking found that black holes are hot. They radiate like hot black bodies, like a stove or something like that. They scatter incident radiation like hot black bodies. There's absorption of radiation, spontaneous emission, and stimulated emission. It falls right within thermal physics. For a Schwarzschild black hole, the temperature is 1 over 8 pi m, where m is the mass of the black hole. So the idea that quantum mechanics and gravity lead to thermal physics and black hole entropy is a deep insight of Hawking that's generally widely acknowledged. And it's an insight that takes us in interesting directions, which have still not been fully understood. Wick rotation is naturally suited to exploring thermal physics because of the connection between inverse temperature and imaginary time. In fact, it's part of a program which has been going on for a long time of the geometrization of physics. We have geometrized mechanics, gravity, electromagnetism, Yang-Mills theories. But this tells you that perhaps you can also geometrize thermal physics and entropy. So let me give you an argument, a very well-known argument from Gibbons and Hawking, and then I'll criticize the argument by applying it to a situation where it doesn't work as well. The argument is the following. Take the Schwarzschild metric and take the time which is defined by the Killing vector, the static time. What I will do is to replace this by I tau, or minus I tau, use the Schwarzschild time to Wick rotate, and get a Euclidean Schwarzschild metric. And let me just say that this angular part is not going to be very important. I'm going to ignore it. You're effectively in 1 plus 1 dimension here and in 2 dimensions here. So the line, if I look at the TR plane in 2 dimensions, the horizon is at r equal to 2m. There's a black hole region over here, and this is the exterior. Consider this line here. This line, if you look at the metric, you'll find it's actually a point. Because if I put r equal to 2m, this thing vanishes. So the entire line has got 0 length. So it must be a point. And if I take a small distance away from the epsilon distance away from the horizon, and look at this line, that line has to be a circle encircling this point. So this argument leads to the idea that perhaps we need a circular identification of time. And If you carry out the algebra, the geometry near the horizon can be written by a change of coordinates in this form, where this theta is tau upon 4n. If theta is chosen periodic, if theta is chosen periodic with period 2 pi, we get no singularity at the origin of this coordinate system. Otherwise, you get a singularity. So if you want to avoid a singularity, you declare that tau is periodic with theta is periodic with period 2 pi, or then tau is periodic with period 8 pi n. And it's very simple to note two things. One is that we take a piece of paper and fold it like this. This is avoiding a conical singularity, whereas this is having a conical singularity. You'll also notice that if I take an arrow here, and I make sure that all these arrows are parallel to each other according to the local geometry and local parallel transport. But when you put it together, you find that the parallel transport of this vector is different. These two vectors are not in agreement with each other. So the holonomy around a curve determines is a detector for the presence or the absence of the conical singularity. So this can be thought of as deriving the Hawking temperature by Euclidean methods. You will appreciate that the actual derivation of Hawking uses entirely different methods, which are based upon particle scattering. And this is a completely different, more geometric way of surprisingly getting the right answer. Now, when you apply the same idea to the Kerr metric, which is stationary and not static, you find that you get complex metrics. It's no longer a Euclidean rotation, but it's actually a complex metric. That comes about because there are cross terms, dt, d phi, in the metric that come about because of the rotation. So if you complexify time, you get metric which has got real parts it's got an imaginary part in the cross terms. In fact, no global time function exists in the Kerr spacetime. This is a further subtlety, because this killing vector, the killing vector which is time-like at infinity, actually becomes space-like in the ergo region. So the Kerr is not even stationary in a strict sense of the term. So there is no global time function, and the time-like killing vector is not hypersurface orthogonal, and the time-like killing vector that's good at infinity becomes space-like in the ergo region. So the metric has explicit time dependence. It's not even stationary. Maybe I'll pause here in case anybody has some remarks on this criticism of the standard Wick rotation. Yeah, so that killing vector is space-like at infinity. Yeah, there are people who do that. You're right. So then you're going with imaginary rotation also. Yeah. So I'm proposing a different solution. Yeah. Right. Yeah, you can do that too. No? And in fact, there are people who are not bothered by this. They're saying we're quite happy with complex metrics. So yeah, so I'm going to propose a different solution from the one that you have. So just to bring out these problems again, suppose you look at de Sitter space, and similar things work also for anti-de Sitter space. And just look at this one. This is the form of the metric written in some particular coordinate system. H is a constant which would be interpreted as Hubble's constant, which is a constant in this cosmology. Now, if you take t to I tau, you find that the metric becomes complex. And over complex metrics, it doesn't make sense to talk about signature. All metrics are the same. They're Euclidean or Lorentzian. There's no distinction of signature. Now, you take the same metric and write it in a slightly different form, where the spatial sections have got negative curvature. And then you perform a Wick rotation, you find a Euclidean form. So it looks like coordinate space Wick rotation is coordinate dependent. It depends on which coordinate system you choose. So instead of this, yeah, the standard one, yeah. Yes. Take a coordinate, take a time function, and rotate it. Instead, I'm going to explore tangent space Wick rotation, and here's the idea behind it. Well, before I explain the idea behind it, let me tell you what the problem is. The problem comes from the subtleties of the nature of time in GR. Time in Newtonian physics is a state function. It's a universally given function on the space-time manifold. In relativity, time is a path function depending on your history. This leads to things like the twin paradox. Minkowski time, you choose an inertial observer, and Wick rotation is the same, regardless of the observer. And similarly, in Schwarzschild spacetime, one can choose a static observer. And what you're doing is taking the stationary observers and using their time suitably rescaled to allow for the redshift. Now, I want to generalize the idea of Wick rotation so that it works for a larger class of spacetimes. So we all know that instead of the metric, one can go to a local frame. A local frame is a description of an observer who's only concerned with a small patch of the spacetime. And in fact, this is very much in the spirit of GR, where the equivalence principle tells you that local physics is extremely local. That is, you can forget about the curvature. You can just look at what's there. You take the metric and write it in terms of tetrads. And this is the idea of the spacetime as viewed by local observers. They would, of course, define the time as the time function as we normally do. But now, instead of taking a time function, I will just take the E naught, the first of the zeroth component of the tetrad, and change that to IE. Or equivalently, I'll take the metric and change that from Minkowski to its Euclidean version. So if I do this at every spacetime point, what I have is a metric which is clearly Euclidean, and it's real. To motivate this a little further, in coordinate space Wick rotation, in theories with tensor matter fields, one thinks of the coordinate space Wick rotation as a complex coordinate transformation, and then one has to also Wick rotate the tensor fields. For example, if there's an electromagnetic field or a Yang-Mills potential, A naught would go to I times A naught. So you would have to complexify all the fields, rotating the tensor components to imaginary values. Now, in theories with Spinor fields, a similar thing is true. Wick rotation also means that you have to Wick rotate the Spinor fields. Now, to handle Spinor fields in curved spacetime, one does have to introduce tetrads. So one might as well introduce tetrads from the beginning and do everything in terms of tetrads, Wick rotation also. The Cartan structure equations tell you about the holonomy. This A is the gravitational version of the holonomy, the vector potential. And this equation determines the connection in terms of the tetrads. It happens to be antisymmetric because it's an SO3-1 connection. Now, this has got the same info as the spin connection, the Newman-Penrose coefficients, which are normally used when talking about GR and the spin and the Kerr metric. The holonomy of the metric is basically the parallel transport, very similar to what I showed with the arrows. So the Wick rotated frames yield an SO4 holonomy rather than an SO3-1 holonomy. So what we're doing is doing the complexification within each tangent space, and it doesn't quite fit together, but it doesn't matter. Tetrads give us a way to Wick rotate spacetimes and arrive at real Euclidean metrics. No, you will see that it works perfectly okay. If there are no global obstructions, you can actually, okay, let me just answer that point in a second. So, yeah, so let's suppose that I'm doing it locally at every point. If there is no global obstruction to doing this, you're back in the earlier picture where there is a global time. But this method works even if there are, as you say, global obstructions. So that's the generalization. Even if there is, the procedure that I'm going to follow is simply to take the local tangent vector and Wick rotate the tangent vector. Okay? So this is done in each tangent space. Now, if they mesh together, if it turns out that the tangent vectors are hypersurface orthogonal and killing, then you actually are back at this situation, standard Wick rotation. But this is a generalization. So I'll just go ahead, and I think it'll become clear in a few minutes. So we can also express the final result entirely in terms of metrics without bringing in frames. We don't need a global time coordinate, but we can make do with slightly less structure. What we do need is a local notion of time in each tangent space, a time-like future pointing vector field, UI. The Euclidean metric is given by just taking the old metric, which is Lorentzian, and adding 2 UI uj. And this is a real Euclidean metric. We use a time-like unit vector field. Yeah, in fact, we'll see some interesting things about that later. Yeah. The inverse metric is given by this formula. In the special case that U is Killing and hypersurface orthogonal, that is to say, multiple of U is Killing and hypersurface orthogonal, these local notions of time mesh together to give a global time coordinate, and our method reduces to the usual Wick rotation. Not Killing. Time-like vector all over space-time. Yes, yes. Exterior, for example. Yes, yes. Only in the exterior, that's right. Yeah, that's right. In the region of space-time of interest, this is doing something else. But if you do it there, you would have to also Wick rotate the shift, which would then bring in imaginary terms here. Yeah. Yeah. So let's go on and see what it does. In fact, I'll do a few examples to illustrate what it does. So in fact, there's no global time function for Kerr. We've been over this before. Instead of a local frame which defines time at each tangent space, we use a local frame, and that defines a local time direction. The local time directions don't mesh together to give a time function. That's the point that I was making. And that is exactly the generalization. Yeah. SO3. Yeah. Yes, yes. Yes. Right. That's the prescription. Yes. Right. So I am working on the frame bundle. Euclidean section. Yeah. Yeah. Okay, so the null generator, if you suppose you apply this to Kerr, you'll see that it goes through perfectly well. And I won't go through Kerr, I'll go through a much simpler example, which has the same physics in it. The null generator of the horizon projects down to a point in Euclidean spacetime. That's because the null generator is a null curve. And if you choose a vector field U, if you choose the U in such a way that U is everywhere, U is a time-like vector field, whose integral curves are in the exterior of the Kerr, then what you find is that the null generator of the horizon projects down to a point because it actually becomes a zero vector. The tangent vector to the null generator projects down to 0, so the whole generator is a point. Now you look at another curve which just hugs the horizon. In fact, those are the kind of curves which are responsible for Hawking radiation, the particles which hug the horizon for a long time. And then you find that this curve projects down to an infinitesimal circle near this point. Now, if I have an infinitesimal circle, and in the limit that the circle goes to a point, the holonomy has to go to 1. It has to become trivial. So that condition enforces some global identifications in the Kerr spacetime, and it gives the correct Hawking temperature. So the argument correctly gives you the Hawking temperature for Kerr, at the same time giving you a completely Euclidean Kerr metric, which of course depends on the U, but the temperature does not depend on the U. The physically important thing, the temperature that you get from this argument, doesn't depend on the explicit choice of U. It only depends on the U, which is very close to the horizon. So this is a picture showing the Kerr horizon. These red lines follow the integral curves of the vector field that Suvrat was talking about. This is d by dt plus omega d by d phi, where omega is the angular velocity of the horizon. So these lines go up around like a barber's pole. And the green curve shows a curve which is just outside the horizon and hugging it. And in the Euclidean picture, the red curve becomes a point. Red curve becomes a point, and the green curve becomes a circle encircling that point. And if you want to avoid a conical singularity, you would have to make sure that the holonomy of this curve is trivial, or rather the Euclidean holonomy of that curve is trivial. So you have an SO31 holonomy, but when you Wick rotate, you get an SO4 holonomy. Within SO4, there are compact directions where the group element actually comes back to the identity, and that's what we're requiring. So in particular for the Kerr metric, we get the right Hawking temperature. And this work has been published in Classical Quantum Gravity. It's also up on the archive. Yeah. Sorry, we have time. That is the reason. Yes, that's exactly the reason. Yes, yeah. In fact, I'm going to do an example on the board because I have some time. I'll do an elementary example. See, the thing is that the Kerr metric, as everybody knows, is the subject of a fat book by Chandrasekhar, where you talk about a lot of spin coefficients. The algebra is quite complex, but I'm going to choose a very elementary example and do the same calculation there. And it's exactly as you're saying. That's true, but the asymptotics is built in because the asymptotics, it does come in because the t variable is, I mean, there is, when you do some identifications, if you want to avoid kicks, there's got to be, it has to be an isometry. So in that sense, the t variable is still there. We'll come back to that. That's an interesting question. We'll come back to that also. Okay. So before I do the example, okay, I think I'll come back to the slide later because it's got thank you at the bottom. So I'll just write down a particular metric. I'll make these 2 points and then I'll stop. Yeah, that is an interesting direction which I have not explored, but it looks like it's worth trying. No? Yes. The angular velocity. Yes. Right. No, see. So I'm going to consider a very simple example, which is in 1+1 spacetime. And the metric looks like this. I should write down the form of V of R. V of R is equal to square root of 1 minus 2gr. And this is defined in the region 0 less than t, minus infinity. And 0 less than r less than 1 upon g. And also one can extend the metric by a simple coordinate transformation to the region where r is greater. So you can take the TR plane, this is t and this is r, and use this coordinate system up to r equal to 1 upon 2g, and use a Rindler coordinate system overlapping for the rest of this thing. What I've written down is basically a Pine-Levé form of the Rindler metric in order to bring out the points that I'm trying to make. So the Pine-Levé form is perfectly non-singular even at the horizon, unlike the Rindler form, which is singular at the horizon. So here, suppose I were to use the tetrads, which come up naturally here. E0 is equal to dt, and E1 is equal to dr minus V of r dt. Then you find that the metric is quite clearly Euclidean. And also, this line, this line, I should draw it in. This line, which is the horizon of Rindler, this line projects down to a point, and a curve which is very close to the horizon is a circle enclosing that point. Now, when we work out the holonomy of that connection, the Cartan equation, which really looks like this, can be solved quite simply, and you find that the connection is given by derivative of this function v into dr minus v of r dt times k, where k is the generator of the boosts. It's got this form, matrix form 0, 1, 0, 0. So in 1 plus 1 dimensions, the Lorentz group has got just one generator, and that's the generator k that comes here. Now, the holonomy can be written as exponential of integral of k times v prime of r, just doing this integral over the curve gamma, which is approaching the horizon, minus v of r dt, and that turns out to be exponential of minus v squared over r prime beta k over 2, where beta is the identification that you make between this point and that. The beta is the separation between the initial and the final point, which you make in order to get this curve into a circle. And when you require that this is equal to 1, what you find is that v squared of r prime beta over 2 is equal to 2 pi, and that gives you beta is equal to g over 2 pi, which is the under temperature. So it's exactly the same argument in Kerr. It looks considerably more complicated because the working out of the spin coefficients is much harder, but that's all in the paper. But you get the same answer that you would expect. Now, I'd like to also just address Rajesh's question. So if you just look at the problem of a particle in a potential, you had this, you had the picture that under Wick rotation, the potential reverses itself. So when you go to Euclidean time, you get the solution of the equations of motion with an inverted potential. So a very similar thing happens here in this case. If you take a metric G, you find that the Wick rotated metric does not satisfy the same Einstein equations. But what it does satisfy is quite interesting. There's a choice of coordinates, and there's a choice of the U vector field. I mean, now you have the freedom. Now you have this extra thing which you can use. You can choose it as you like. Earlier we had the choice of time, which was more restrictive than the choice of U. But now that we have this extra freedom, we're not requiring that it be killing. We're not requiring that it be hypersurface orthogonal. But we can also choose whenever we like to have either make it killing or hypersurface orthogonal. In particular, I'm going to choose U to be a geodesic congruence. Suppose I do that. I can choose it instead of being killing and hypersurface orthogonal to be geodesic and hypersurface orthogonal. That's possible in any plane. It's called a synchronous plane. That is, I take a set of particles and I let them follow geodesics, and I take the time. Basically, this follows from Hamilton-Jacobi theory, that you can always find such a frame. When you use such a frame, you find out that the Hamiltonian of GR, which was previously given by pi squared over 2 plus 3 potential, the Einstein's equations were basically generated by this Hamiltonian, where this was the kinetic term and that's the potential term. What you find after Euclideanization is that the potential term reverses. So it is what you would expect in this frame. It's what you would expect for the potential term, reversing of the potential. Yes, yes. Yeah, yeah. No, you look for Euclidean solutions. Yes, yes, yes. Yes. Yeah, no, in fact, yeah, that is true. Even in the usual method of doing things, there are some instantons which people like Gibbons generally use a very, um, well, they take a liberal attitude towards what metrics are you integrating over. Okay, I'll just say a few words and then I'll stop. Yeah, so they allow all kinds of complex metrics, and only the real solutions they think of as instantons. I find it a slightly disturbing attitude that they are not, I mean, really once you try to get all the Euclidean solutions, I mean, there should be, see, one attitude to take is simply that this is a analytic continuation. So you don't really care about what kind of solutions you get, whether they're Euclidean or not. You know? But I think it's often useful to insist on getting a Euclidean solution and interpreting it as an instanton. I mean, that's just a matter of taste. Maybe I'll just finish up very quickly and then I'm sure there'll be a few more questions. So can generalize the notion of Wick rotation to frames so that we make use of less structure to allow a more general notion of Wick rotation consistent with the nature of time in GR. All we need is a time-like killing field. It need not be killing or hypersurface orthogonal. It leads to real Euclidean metrics and not complex ones. So that's basically the end of my talk. And I think I finished 2 minutes ahead of time. Maybe we have time for 1 or 2 questions. Yeah. Yes. Yeah. Yes. I think so. I think it would. I've not done it. I've not done it for many examples. I mean, I'm sure there are more examples to try, but in the elementary examples, it certainly does give you the right answers. Yeah. Yeah, yeah. I think it still has to be investigated, but I think it should work. You know? Right, right. You have to add the right boundary terms, the extrinsic curvature of the boundary and things like that. Yeah. In fact, some other work with Sumati, we are talking about things like that also. Not for the Wick rotation, but in standard GR. I just want to make another comment. Sumati raised this point about looking at things which are not quite Schwarzschild. That is, perturbations of Schwarzschild. In that case, you would find that the thermal circle has got different radii at different points of the horizon. Yeah? And I'm wondering, I'm not very sure about this, but it may be possible to address deviations from thermal equilibrium. Because having having a uniform temperature is a sign of thermal equilibrium. Maybe some kind of non-equilibrium physics, statistical physics can also be addressed geometrically by using things like this. So I think I've run out of time. I've got run out both Euclidean and imaginary time.
The fact that the conformal mode is in the usual Euclidean, the conformal mode is unbounded from.
Yes, yeah, yeah.
Does this then?
I don't think it really solves it. I think that's a genuine problem having to do with the Euclidean approach. Yeah, and the attitude one sometimes takes towards this is that this is probably low energy description of some other theory, which yeah. So in that sense, one doesn't expect this to be the Euclidean Euclidean approach to quantum gravity, I don't think is likely to succeed, but there is a lot of truth in the approach. And we should definitely try to keep what there is.
I was wondering whether flipping the sign of the
potential. Yes.
Yeah. Could
could help.
That be a fix of the problem? I mean, what it means, I don't know.
Yeah.
But you can imagine maybe Hamiltonian formulation of Euclidean theory in which you sort of by hand do this and then see whether that makes some sense.
I'll think about that. I've not really done that. It's a good suggestion. So I'm sorry, I think you should